Let's say we want to paint parts of the white plane blue, but there's a rule. No two blue points are allowed to be exactly 1 unit apart. In this video, this line with the two circles will always represent a unit length. The circles are like little magnifying glasses. They show the color of the points at each end. When both circles turn blue, we found a pair of two blue points exactly 1 unit apart, breaking the rule. Here is a coloring that obeys the rule. No matter how we take a unit interval of the plane, at least one of the endpoints is white. We call the blue part of such a coloring a one-avoiding set. This video is about a question first asked by Leo Moser in the early 1960s. What fraction of the plane can we color without breaking the rule? In other words, what's the largest possible density of a one-avoiding set? The video has 3 main parts. First, we showcase a quite dense one-avoiding set, the record holder since 1967, with a density of 22.93%. Second, we present some simple and fun elementary arguments that show why the density of a one-avoiding set cannot be too large. Third, we introduce the core ideas behind our recent proof that the density must be less than 1/4, settling a well-studied conjecture by Paul Erdős. The plane is infinite, so it's not even clear that the density of a subset of the plane is a meaningful concept. The question can be made precise with a bit of measure theory. But for the purposes of this video, let's just sidestep the issue. Imagine that the question is asked about a very, very large piece of white paper, so large that the areas near its boundary have a negligible effect on the densities we consider. With the right definitions, it's not hard to prove that this does not fundamentally change the question. A unit diameter circular disk without its boundary is a one-avoiding set. 2 colored points are always closer than 1, but its area is infinitely smaller than the whole plane, so its density is 0. We can do much better by packing such disks in an infinite triangular grid, making sure that there is a gap of length 1 between them. It's not hard to determine that the density of the blue area is pi divided by 8 times square root 3, approximately 22.67%. Another related idea is to pack unit diameter hexagons. The advantage is that we can pack them more tightly. The disadvantage is that unit diameter hexagons have smaller area than unit diameter disks. All in all, the hexagon packing has a smaller density than the disk packing, 21.54% versus 22.67%. In 1967, Hallard T. Croft has managed to improve the disk packing construction by combining it with the hexagon packing construction. If we pack the disks slightly denser, some unit distances appear across adjacent disks, but we can get rid of these by slicing off the affected parts. The resulting shape is an intersection of a circular disk and a regular hexagon. Here is a close-up of the intersection. There's a trade-off here between packing the shapes denser and slicing off as small area as possible. Let's zoom out now to get a fuller picture. From now on, the zoom level will not change, which is important to mention because it will look like it does. But the camera is static. It is the gap between the disks that changes during the animation. Croft has determined that among these sets, the maximal density is achieved when the perimeter of the shape is exactly 50% circular arcs and 50% segments. This shape is called Croft's tortoise. This gets us a tiny improvement over simply packing the circular disk, from density 22.67% to 22.93%. Croft's tortoise is the densest known one-avoiding set. Since 1967, no one has managed to improve it, nor has anyone proved that it is the best possible. What's the largest possible density of a one-avoiding set? The second and third parts of our 3-part video will deal with results showing that high-density sets cannot be one-avoiding. In 1985, Paul Erdős conjectured that the density must be less than 1/4. That is, it's impossible to paint a quarter of the plane blue without having two blue points exactly 1 unit apart. Interestingly, he did not go further and conjecture that Croft's construction is optimal, and we don't know why. Perhaps he thought it was too ad hoc to be the best possible. In any case, that turned out to be fortunate for us. Our team has managed to prove Erdosh's conjecture. Whether Croft's construction is truly optimal still remains an open question. The rest of the video introduces more and more new ideas until the proof becomes within reach. Interestingly, the number 1/4 turns out to have real mathematical significance here. Let's warm up by proving that a one-avoiding set cannot have density larger than 50%. Let's say someone brings us a one-avoiding set A, the blue set. We translate it by 1 to the right, call the translated version B, and color it red. I claim that if the blue set was indeed one-avoiding, then the blue and the red sets do not intersect. We prove this claim by contradiction. If there is a point in the intersection of A and B, let's translate it back to the left by 1. The resulting point is in the set A, but the point on the right is also in the set A. We have spotted our disallowed distance 1 pair reaching a contradiction. A and B are disjoint. They have the same shape, hence same density. This density cannot be greater than 50%, otherwise their union would be greater than 100%. We introduced the argument using a translation to the right, but of course it works with any direction. We can sharpen this argument the following way. Now we translate by 2 sides of a regular unit triangle, getting translated versions B and C. By the previous argument, A and B are disjoint. Also, A and C are disjoint. But even better, B and C are disjoint, because C is a translated version of B, translated with the third side of our regular unit triangle, so we can invoke the previous argument a third time. But if A, B, and C are all pairwise disjoint and have the same shape, then their density cannot be larger than 1/3. This line of attack gets stuck here, because to prove 25% this way, we would have to put 4 points on the plane so that any 2 of them are at distance 1 from each other. This is only possible in 3 dimensions. To make further progress, it's helpful to reformulate the argument. Let's imagine that we drop a translated version of the unit triangle on the plane, choosing the translation randomly. Randomly dropping a set on the plane is not well defined in general, but remember, we are on a very large rectangle now. It is meaningful to choose a uniformly random point of that rectangle and move one of the elements of the set there. Moreover, there is a negligibly small chance that this random point is near the boundary where it could cause issues. Of the 3 vertices of the randomly dropped triangle, at most one can be blue, otherwise we have spotted a unit distance. From now on, we will often do the following in the video. Randomly drop a finite set onto the colored plane and observe how its elements are colored. We will call such sets probes because we use them to examine one-avoiding sets. When visualizing probes, it is worth highlighting the unit distances. This defines a graph, with the elements of the probe as vertices, and with the unit distance pairs as edges. We call such graphs unit distance graphs. Really, they are still just finite sets of points on the plane, but now with the unit distances highlighted. In 1961, Leo Moser and his brother William Moser introduced the Moser spindle. By replacing the unit triangle with the Moser spindle, Croft managed to improve the 1/3 bound to 2/7. He did this using the same idea of randomly dropping a small translated set onto the plane. For our purposes, the crucial property of these 7 points is that no matter how we choose more than 2 of them, there will always be a unit distance between some pair of chosen points. This means that when we drop randomly translated versions on the plane, there can never be more than 2 blue points out of the 7. Otherwise, we would have spotted a unit distance. By the same argument as the one used for the triangle, this proves that the density of a one-avoiding set cannot be larger than 2/7. Some standard notions of graph theory will be handy here. An independent set of a graph is a subset of the vertices with no edges between them. The independence number of a graph is the size of its largest independent set. As we previously discussed, the independence number of the Moser spindle graph is 2. The independence ratio of a graph is the fraction of its vertices that can be chosen so that no edges lie between any two of them. In other words, it's simply the independence number divided by the number of vertices. Armed with the definitions of the unit distance graph and the independence ratio, we can generalize the Moser spindle argument. For any unit distance graph in the plane, its independence ratio is an upper bound on the density of any one-avoiding set. Our goal is now to find a unit distance graph with a low independence ratio. It is surprisingly hard to beat the Moser spindle in this competition, but in 1992, Fisher and Ullman managed to do so by placing many Moser spindles in a grid-like pattern. An extra trick employed here is that some of the points forming the graph are included multiple times. This is allowed by the argument, since it does not rely on the distinctness of vertices. Their graph improves the bound yielded by the Moser spindle, but just a tiny bit, less than 0.5%. Here is the Fisher-Ullman graph in use. For a long time, the main strategy when trying to solve Erdosh's conjecture was to construct a unit distance graph with a low independence ratio. Indeed, researchers kept inching towards Erdosh's goal by building larger and larger graphs in clever ways. The difficulty was that the calculation of the independence ratio became harder and harder, even using clever algorithms and large computers. Now we have finally arrived at the third and last part of the video, about our team's 2023 proof of Erdosh's conjecture. This proof also uses unit distance graphs as probes, but it extracts information from them in a more careful way. So instead of, say, 1,000 element probes, 30 element probes already yield good results. Looking at our probes, they are much less symmetric and pleasant-looking than the probes from the previous part. Ours were found by large-scale computer search. In a well-defined sense, they are compressed versions of astronomically large, highly symmetric probes. This time we will use the random drop idea in a more careful way. We start by adding a small twist, applying a random rotation to the graph before dropping it. On its own, this doesn't help. The upper bound on the number of blue points remains the same. But the random rotation idea becomes useful when combined with another, keeping more detailed records of the probe's coloring patterns. Instead of merely counting the number of blue points in the probe, we will pay attention to the details of the coloring. Let's say our probe has n vertices. When we repeatedly perform the random drop, we can count how many times each of the 2 to the power of n possible colorings arises. In the limit, as we repeat this process infinitely many times, we can talk about the probability of each coloring. What can we say about these probabilities? On the last screen, we hinted at an important new notation. For any probe and any of its colorings, if we put the colored probe into a pink box, that turns it into a number. Namely, the pink box represents the probability that, when the probe is randomly rotated and randomly dropped onto the plane, its coloring is compatible with what the probe observes on the colored plane. What you see on the screen is a preview of the rules we'll explore in the next few scenes. The probabilities clearly depend on the choice of the blue set. But as we will soon see, they obey some simple but powerful rules that are true regardless of how we choose our one-avoiding set. Even better, these rules can be expressed as linear equations in terms of the probabilities. Let's start with a trivial but important rule. If the coloring has an edge with 2 blue endpoints, its probability is 0. Otherwise, our probe has spotted a distance 1 in the supposedly one-avoiding set A. So far, we have assigned probabilities to blue and white colorings of the probe. To go further, we introduce a third color, gray. If we paint a vertex gray, it means that we don't care whether it's blue or white. We can assign a probability to any blue-white-gray coloring of any probe. For example, a fully gray probe has probability 1. We can now introduce an elaborate visual arithmetic on the coloring probabilities. The second rule is that we can get the probability of a blue and gray coloring by summing the probabilities of all the blue and white colorings that are compatible with it. The third rule is that gray vertices do not matter. We can remove them. Removing them changes the probe itself, but it does not change the probability of the coloring. This is our first and only rule that has two different probes on the two sides of the equation. The fourth and last rule is that two colorings have the same probability if they are congruent. After the random rotation and translation, they become indistinguishable, so their probabilities must be the same. Let's see all the four rules at the same time. From the last two rules, it follows that two coloring probabilities are equal if the blue subsets are congruent, and the rest is gray. For example, these are all equal to each other. All of them are equal to the probability that two randomly chosen points in distance square root 3 are both colored blue. Let's now show the rules in action using a 9-vertex probe. Later, we will talk about how it was found. Its independence ratio is an uninteresting 1:3, but it gives a pretty good bound when we make use of all the knowledge we have built up so far. We can introduce variables for the probabilities of all 2 to the power of 9 possible blue and white colorings. Thanks to our Rule 1, only 50 of these probabilities are non-zero, those corresponding to independent sets. We can write up all possible rules such as the above as linear equations over these variables. The probabilities depend on the set A, but crucially, the rules themselves are true for any one avoiding set A. Here is the graph in use. Okay, but what does all this have to do with the density of our one avoiding set? Let's repeat the random dropping from the previous scene, but this time using a probe with a single vertex. The probability that this probe is blue is simply the density of the one avoiding set. And thanks to our rules, that quantity can be written up by summing up some of our variables. Now we can ask, when the probabilities satisfy all our rules, which values of the blue set's density are possible? This question belongs to the field of linear programming. Linear programming takes a system of linear inequalities and figures out what values a variable can possibly have when all the inequalities are satisfied. For example, in the toy example shown, the inequalities imply that z must be less than or equal to 13. A key difference from this simple example is that our systems involve more than 2 variables, specifically 1 variable for each independent set of the probe. In the previous example, a 9-vertex graph, there were 50. Larger probes generally yield better density bounds. For 30-vertex probes, the number of variables can reach 1 million. Fortunately, specialized software exists that can handle such massive problems efficiently. Every probe yields a density bound, but which probes yield a good density bound? It turns out to be surprisingly difficult to predict this. Even after examining hundreds of unit distance graphs and the density bounds they yield, we still lack a clear intuition about which graphs are good. It's even harder to come up with good probes using pen and paper. The best we could manage was this one. Our graphs were found by a computer. Starting from the Moser spindle, we had the computer incrementally add and remove vertices, while it monitors the bound each resulting probe achieves. Our complex search algorithm methodically combs through millions of probes. For each probe, it solves a system of linear inequalities to determine the density bound that it yields. The system can potentially have millions of variables. Eventually, after running for weeks on a supercomputer, the search algorithm discovers some very good probes. Note that the animation does not show the millions of probes checked, only how a single good one was constructed step by step. Our search found better and better density bounds as the size of the probes increased. Then something very unexpected happened. The search found a probe yielding a density bound exactly 1/4, and then it got stuck, not progressing any further. Finally, we gave up and stopped the search. At this point, we are frustratingly close to proving Erdosh's conjecture. He asked us to prove that the density of a one-avoiding set cannot reach 1/4, and we have managed to prove that the density cannot exceed 1/4. This brings into sharp focus the fact that Erdosh formulated his conjecture the way he did. He didn't explain his reasoning when choosing 1/4. What did he know when he picked this number, and how is it related to our observation that our method gets stuck at exactly 1/4? We don't know. One extra idea is needed to push this over the edge. It comes from harmonic analysis, and while we can't fully explain it here, we can at least give some hints about how it works. Let us introduce the autocorrelation function of a one-avoiding set A. For each non-negative x, this function assigns the probability that when we randomly drop an interval of length x onto the plane, both endpoints land in A. In the language of our visual arithmetics, it's the probability of this probe. For example, f1 is 0 because the set is one-avoiding, and f0 is simply the density of the set. It turns out that this function can be well approximated by the weighted sum of so-called Bessel functions, using only non-negative weights. The non-negativity of a weight is a constraint that can be added to our set of linear inequalities. Let's summarize the video. In this figure, the blue part of the number line shows one-avoiding set densities that are known to be attainable. The red part shows densities that are known to be unattainable, and the black part in between marks the limits of our current knowledge. We learned how to create high-density one-avoiding sets using hexagons and disks, and then combined them to get Croft's tortoises. We first proved the easy claim that one cannot color more than half of the plane in a one-avoiding way. We then improved this bound successively using graph theory, but still couldn't reach the 1/4 density bound that Paul Erdős asked for. Then we analyzed how probes randomly dropped on the plane intersect with our one-avoiding set, and reached the 1/4 bound using gigantic systems of linear inequalities. Then we brought analysis into the mix, which helped to improve the 1/4 bound to strict inequality.